Okay, this is a review for test 3. This is your last exam for your coursework before the project grade, and then you're finished in the course. Okay, for the first question, it's just a basic question talking about normally distributed items. So in this case, it's salaries of workers. And when we say normally distributed, it means it looks like a bell curve. And that bell curve should be symmetrical, and we put the mean as the highest point on that bell curve. So in this case, the mean, they said, is 1600. And it turns out that any normal distribution has this trait where if you go 3 standard deviations above the mean, so that's 1 standard deviation, that's another standard deviation, and a third. And similarly, if you go 1, 2, 3 standard deviations lower than the mean, we're going to capture most of the data. And in fact, being normally distributed basically gives us this. 34% of the people will be in each of these sections, which are plus or minus 1 standard deviation away from the mean. And then 13.5% will be within 1 to 2 standard deviations away from the mean. And then lastly, we can say within 3 standard deviations, 2 to 3 standard deviations of the mean. This is actually 2.35% here and here. Now, what does that mean in terms of answering our question? So let's look more at the question. And it says the standard deviation, 1 standard deviation is 150. So if we're going to add 150, that would make this 1750 here, 1900, adding another 150, and then 2050 would be 3 standard deviations. And we'll do the same thing by subtraction. 1600 minus 1 standard deviation of 150 would be 1450. And then minus another 150 would be 1300. And then here, this would be minus another 150, 1150. So now when it asks, well, which 2 values does 95% of the salaries fall between? Turns out that 95% of the salaries are in this range. So 95%, if you added up 13.5 plus 34 plus 34 plus 13.5, you would get 95% of the data falls within plus or minus, so it's going to be the mean plus or minus 2 standard deviations will give you 95% of the data. And in this particular case, what numbers are those? 1300 and 1900. So it turns out that if I say that the salaries are less than 1900 and greater than 1300, then I would capture 95% of the workers in the workshop. Okay, let's look at the next question. 68% of the salaries. Well, it turns out, and this is true for all normally distributed data, that 68% of the salaries say if you take the mean and you just plus or minus 1 standard deviation, you will capture 68% of the data. So that's talking about these 2 places. So if the salaries are between 1750, that's the mean plus 1 standard deviation of 150, and then the mean minus 1 standard deviation of 150, so a range between 1450 and 1750 would capture 68% of the salaries. And now lastly, 99.7% of the salaries. Well, we know just because this is the fact for all normally distributed data that 99.7% of the salaries or of the data would fall between the mean plus or minus 3 standard deviations is going to capture 99.7% of the data. And that's true for all normal distributions. So you can think, okay, plus or minus 3 standard deviations away from the mean captures almost everyone or every item in the data. So in this case, that would be between 1150 here and 2050. So the salaries between 1150 and 2050 would capture nearly all of the employees in the company. Okay, this next question, all of these questions, by the way, will have to do with normal distribution. So it always makes sense to draw the picture and see what they're telling you. The mean is 335. Okay, and the standard deviation is 50. What percent of the students lie between 285 and 385? So I'm going to draw that picture, 285 and 385. In fact, that looks to me like it's exactly one standard deviation, 285 and 385. Let's double check here. I think that's the case. If you did, I'm sorry to say, let me start again. If you did the mean plus one standard deviation, plus one standard deviation, and then the mean minus one standard deviation, let's see what we get. 335 plus 50 is 385, and 335 minus 50 is 285. So it turns out that they're asking for something that we already know. If we have one standard deviation to the left, one standard deviation to the right, we know that we are capturing 68% of the data. So we can just directly know the answer is 68%. Okay, but a lot of times in a question, it's not as simple as that. So why is it not as simple? Because the numbers they're giving us to test might not fall on a standard deviation, like a clean number, like 1 or 2 or 3 standard deviations. So if we want to figure out how many standard deviations it is, we say, all right, let's use a z-table. So you find out the z value, which is basically the number of standard deviations, and the formula is this. You take the value they're asking about, subtract the mean, and divide by the standard deviation to see exactly how many standard deviations we are away from the mean. So for example, for 485, you would do 485 minus 335, divide by the standard deviation of 50, and let's see what we get. And we will do the same for the other value, 185. So we'll say 185 minus the mean, which is 335, divide by the standard deviation, which is 50, and we get minus 3. So for the z value, what they're saying is, on the standard deviation curve, here's the mean, they're saying how many or what percent of employees are above 485, so here, this small sliver, or below 385. So what they're saying is, what percentage fall outside of 3 standard deviations away from the mean? So remember, the mean here is 335, this would be 385, this would be 435, this would be 485, this point right here. And again, another subtract 50, this is 285, subtract another 50, this is 235, subtract another 50, and we get 185. So what is the percentage that fall outside of 3 standard deviations? It's quite small, and as you remember, this percentage right here is 68%. This percentage right here is 95%, and within 3 standard deviations, it is 99.7%. So to be outside of that, it's going to just be 100% minus 99.7%. So we're going to get 0.3% of the data is going to be above 485 or below 185, a very, very small amount. Okay, last question. We will see what percentage of the observations should be below 235. So again, we'll draw this standard deviation, or I can look right here. It's that just below 235. Let's draw this picture. Again, we've got 34%, 13.5%, and over here, if we include everything, this would be 2.5%. And again, here's 34%, 13.5%, and if we include 3 and beyond, this is 2.5%. Again, here's the mean, and we've got 1, 2, 3 standard deviations away from the mean, or 1, 2, 3. And let's shade in what they're asking about. They're asking about being below 235, which this was 285, this was 235. So anything here is going to be exactly 2.5%. Okay, so now we're going to talk about percentages when the z-value, or in other words, the number of standard deviations we are looking at, is not a whole number. So just as a reminder, let me pull up the normal standard distribution curve. And now they're asking, well, what's the area to the left of z equals 3.11? Well, here's the mean, z equals 0. Here's 3 standard deviations. That would be z equals 3. So 3.11 is going to be somewhere here. And we want to know what percentage of the data falls to the left of this. So it's most of the data, in fact. Almost all of the data. If not, we might even just be able to round to all of the data. But what we do is we look on our z curve, and we can actually find the number associated with z equals 3.11. So let me pull that up now. Okay, so we go to 3.1 and then 3.11, and we find that number, which is 0.9991, which if we turn it into percent means 99.91% of the data is going to be less than 3.11 standard deviations above the mean. So that's almost all the data. There's just going to be a teeny bit left on the right. Okay, I cleared all that. Now let's look at the second question. Between z equals minus 1.45, so that's about right there, and z equals minus 1.54, so very skinny range. We want to know what percentage of the data would fall in between those two numbers. Whenever they're asking you for in between, what you need to do is find the correlated z percentage that's to the left and subtract the big minus the small. And because those numbers are negative, I'm going to need the table with negative z numbers. So let me pull that up. Okay, so for negative 1.45, I will find the number. Looks like 0.0735. And for negative 1.54, it looks like this number, 0.0618. So what's happening there on the picture is we found this percentage. This was at negative 1.54, and we get that this is 0.0618. And then we have at negative 1.45 this area, and it's 0.0735. Now what they're actually asking for is the area between those two numbers. So whenever you have that, you must always just subtract the big number, the bigger number, minus the smaller number, 0.0618, and we should get the area in between. And after I calculate, I get a number 0.0117, which is 1.17% of the data would fall between those two z-values, which represents negative or 1.54 standard deviations lower than the mean and 1.45 standard deviations lower than the mean. So this area. Okay, now this question's a little bit different. It's kind of backwards. We don't know the z-value. They didn't tell us standard deviation or mean or anything, but we want to find a z-value so that 41.4% of the data falls to the right. Now, this is important. Let me pull up. Okay, this is the normal standard deviation curve that hopefully you're very comfortable with now. And they're saying we want to find a z-value where 41% of the data is to the right. So that means less than half the data is to the right, which would mean the z-value would have to be somewhere in here. Okay, so what they're saying is 41.4% should be there. Now remember, the z-table is always giving you the percentages to the left. So before we can go look and search on the z-table, we need to know, well, if the right-hand side is 41.4%, what's the percentage on the left-hand side? So I'll say 100 minus 41.4 is 58.6%. So another way of asking this is, okay, if I want 41.4% of the data to be on the right, then I also want 58.6% of the data to be on the left. And we use the left on the z-tables because that's what the z-tables measure. So actually what we're going to be doing is looking on the z-table for a number, and I'm going to use the positive z-table, I can tell from my picture, but I need a number that looks like 0.5860, as close as we can get. So I pulled up the z-table, 0.5860, it looks to me like it would be somewhere right about there. And when you don't have the exact number, you pick the one that is closer. This one is closer, so we would say z should be approximately 0.22 standard deviations above the mean. Where did I get those numbers from? From looking 0.2, and then for the hundredths place, 0.22. Okay, let's look at this next problem. Number of students that attended a festival. It's giving us the mean, it's giving us the standard deviation, and we want to know the probability it falls in a certain place. So always I recommend the very first thing you should do is draw a picture. Okay, so here's our picture, and we've got 335 is the mean. And we're saying somewhere in between 300, which doesn't fall on one of those pretty standard deviation lines, somewhere between 300 and 400 is we want this probability, the probability that the data the number of students at the next festival is in there. So what we have to do first of all is figure out the corresponding z numbers. So for example, for 300, the formula for the z number is x minus the actual mean, the data number minus actual mean over the standard deviation. So we'll say 300 minus 335 divided by the standard deviation is 50, and we get negative 0.7 for the first z number. So z equals negative 0.7. And we'll do the same for the next, which is 400. So I plug in 400 minus 335 divided by 50. And we get a z value of positive 1.3. So then this is just your classic question of what's the area of those regions in between those z numbers. So first thing we'll do is we'll look up the corresponding area to the left when you have negative 0.7 z equals. We need this area, so we look on our table at negative 0.7 z equals to negative 0.7, we get 0.2420. So we're knowing that this area is 0.2420. And we will do the same thing with z of 1.13. Okay, so z of 1.3, sorry, it's not there, it's here, 1.30. So that's 0.9032. And remember, that's measuring this whole distance to the left. That's 0.9032. So when we want this distance in between, we will subtract 0.9032 minus 0.2420, and we will get the area or the probability that the number of students is in between. And we end up with a final answer of 0.6612, so 66.12% likelihood. Okay, let's look at another question, and as usual, it's always helpful to bring up the standard normal curve. And now we can read the question. The average GPA for graduating students is 2.6. You always put the average, the mean, right there in the middle, and the standard deviation is 0.5. So one standard deviation would make that 3.1, 3.6, 4.1, and then minus one standard deviation, that would make this 2.1, and then 1.6, and then 1.1. And let's see what they ask us. What's the minimum GPA for the top 15% students? Top 15 means it will be on the right. The top 15% will be somewhere in here, just as I estimate it. I shouldn't label it there. We want to know what is the value that would make this area here, this area to the right, the top 15%. 15%. So again, remember the problem is the z-curve, or the z-table, gives you the percentage or the probability to the left, the area to the left. So this would be 100 minus 15%, which is 100% minus 15%, 85%. So we're looking on our z-table for 0.8500. And we know just by our logic that this has to be a positive z-value. So let me pull up the chart. And I'm looking for 85%, which looks like it's somewhere about there. We'll just pick the closer one. And I believe this one is closer. And so we can see the minimum GPA for the top 15% of students. Well, it would be a z-score of 1.04. 1.04. Okay, let me just clear the z-table for a moment to make more room. And remember, the formula is that the z equals the actual score minus the mean divided by the standard deviation. Okay, so in this case, we figured out z has to be 1.04. We're trying to find which GPA. The mean is 2.6. And then the standard deviation is 0.5. So we'll do a little bit of algebra, multiply both sides by 0.5. Okay, that cancels. We get 0.52 is x minus 2.6. We'll add 2.6 to both sides. Your calculator can do the algebra for you, but here we go. We get that the GPA, the minimum GPA, would be 3.12. So what does that say? It says if we have a GPA of 3.12 as the cutoff, then 15% of the students, right here, would score higher than that. Okay, now the last question we're going to do has to do with the central limit theorem, which is they give you a normal population, they give you the population mean, the standard deviation, and a sample size. So in this case, they're telling us the population mean is 75, the standard deviation is 5, and the sample is 40. When we have a sample out of the population, the formula for calculating z is slightly different. So let's just do it together. They're saying, well, what is the probability that the sample mean is less than 74? So first thing we must do, the z value is going to be this sample mean minus the population mean. Instead of just dividing by standard deviation, we divide by the standard deviation over the square root of n, the sample size. The bigger the sample size, the closer the data is going to move toward the mean in the normal distribution. It's called the sample error. So let's go ahead and calculate. And we have 74 minus 75 divided by 5 over the square root of 40. And we will get a z value of negative 1.26. And if they're saying less than, again, draw the picture. Here's our z value. Less than is to the left of, which is what we want. So we look on our z table, and I see negative 1.26, 0.1038. So that's what we get. The probability is 0.1038. Probability that we are less than 74. So just a little bit more than 10%. Okay, now we're trying to find the probabilities between 74 and 76. We already know that the z value here is negative 1.26, and we have to find the z value at 76, so it's going to be 76 minus 75 divided by 5 over the square root of 40, and we get positive 1.26. which when we look on the z table, you can see it correlates with 0.8962. So basically the picture we have here, this correlates with the 0.8962, but we already know that here, from this question, correlates with 0.1038, so we will subtract 0.8962 minus 0.1038, and we will get the space in between, which is 0.7924. So that's the probability that we are between 74 and 76 is 0.7924, 79.24% of the area. Okay, so for 76, we already know the z number is 1.26. For 77, we'll calculate the z number, 77 minus 75, all over 5 square roots of 40. We will get the associated z value, which is 2.53. So the task is to just get the areas to the left on our table, and then subtract those two, very similar to what we did in part B. So I'll skip some steps here. And this one correlates with 0.9943, so 99.43% of the areas to the left, and we already know from 1.26, 0.8962, so the space in between is 0.0981, 9.81% likelihood there. Okay, and lastly, what's the probability it's greater than 77? So remember, here's the mean, here's 77. We want to understand the probability that we are here. So we already know, we already have this value at 77 from our previous question. So we know that the z value is 2.53 and the corresponding area from the table is 0.9943. So all we must do to get the probability that we are to the right is subtract from 1, 0.9943. And we will get 0.0057. So a very, very, very small likelihood that the sample mean will be above 77. Okay, hope this helps you in your studies.